Alright, good afternoon, Ramblers. Let's get rambling. We got something new. This is fun, man. This is good stuff. We're out of linears. Finally. Good lord. After, like, what, 8.5, 9 years of school, you are finally to the next function family, and we got this beautiful thing called exponential functions. So, this is something we're going to become really, really familiar with, because this whole world of exponential functions um, is fun. Okay? Uh, the thing about exponential, S-P-O-N-E-N-T-I-L, okay, exponential functions that you have to realize is that these are absolutely nonlinear. So the things we used to know about linear functions no longer even apply. Like they just aren't even part of this world right now, which is not a bad thing. Like we have to learn a new set of rules, which okay, not the best thing in the world, but on the upside of that is that we get to kind of play with like this new kind of model, and this model of what we're going to call these exponential functions. And one of the signature pieces, one of the signature things about exponential functions is how fast they grow. Like they are fast growing. Uh, this is a fast growing equation, fast growing function. Also, I put an asterisk there because also if something grows, it can get smaller. But again, it's going to do so fast. Now, this is probably one of those models that when you look back and kind of think about things in the real world, there's going to be a lot of things that work like this. We talked about the telephone problem today, and I don't know if you guys talked about it in your section, but I was certainly thinking about like Facebook and Twitter and how things totally blow up on Facebook and Twitter these days. Well, the reason they do is one person shares this thing, and let's say they have like 500 followers. Now 500 people know this thing. Let's say each of those guys know 500 followers. So 500 people for each of the 500 people now have this piece of information. You kind of get a sense why things go viral and just totally blow up. Like the Harlem Shake is a good example of that, right? So, um, so we have this situation. Let's go ahead and read it, but we have to keep in mind we're dealing with exponential, not linear. We expect these things to grow very quickly. A flu virus is known to spread quickly. The recent outbreak began with a single contaminated person. There's that person right there. But the number of infected people is increasing rapidly. Each week there are 10 times as many people infected as the week before. Fill out the table to show the number of infected people each week. Okay, so here's a little hint for you guys. It said 10 times more, right? Well, that's how this is showing up. This is a times 10. Well, guess what? To get to our very next thing, that's going to be a times 10 as well. That's going to be 100. Okay, so times 10 again. That's going to be 1,000 people. Times 10 again. That's going to be 10,000 people. Look how fast that spread. In 1 month, the infection went from one person to 100,000 people. You know why I'm afraid of zombies? Well, there you have it right there. 4 weeks, 10,000 zombies, and that's all there is to it. So the question is, well, how many will there be after 5 weeks? Well, that's simple to figure out. We just got to go another times 10, because one more value will bring us to 5. So that will be 100,000 infected in just over a month. Isn't that crazy? Again, this is something to kind of keep in mind that this is why this kind of function family is so special. Things just grow so quickly and out of control. This is just an outbreak of a single contamination. Now we have the city of Columbia infected in just over a month. That's bananas. Okay, so the answer to this is 100,000 people. That's kind of weird. I don't know what that is. If this rate of infection were to continue, about how many weeks would it take for 1 million people to be infected? Well, the best thing we can do is just to continue the table. So that's 100,000. 6 weeks. That's one more times 10. And we're at... So there was a previous week. That's 5. That's week 6. Well, look at that. That's a million people. So this answer right here is just 6 weeks. Again, I know you kind of expect a million people. You're like, wow, that's a ton of people. That's going to take a while. But not if it's growing exponentially. This thing ain't linear. It's exponential. It grows by a factor, multiplication. One person infects 10. They infect 10. Those 100 infect 10 more each. This thing grows rapidly. Really kind of crazy. So even though it has a million people, and for linear, our experience would be that would take a while, this is taking no time at all. And let's check out this one. So a less aggressive strain of the flu is occurring in another area of the country. The outbreak began with a single person, but the number of infected people only triples each week. Now triples, think about that as a multiplication factor. That's going to be a times 3. And that's certainly how it's showing up right here. We have a times 3 going on. So fill out the table. Well, no surprise here, nonlinear, it's exponential. That's a times 3. That's going to be a 9. Here's another times 3. That's going to be a 27. Here's another times 3. That's going to be an 81. Now the question is, well, what's going to be after 5 or 6 weeks? Let's go ahead and fill this out. So that's going to be another times 3. Now, don't, if you can't do times 3 in your head, no big deal. I'm going to do it right here. 81 times 3, that's 3. 3 times 8 is 24. So that's going to be 243 people. Now let's go up to 6. That's another times 3, isn't it? So we're going to take that 243 times another 3. That's 9. Let me see, 12. 3 times 2 is 6. 7. So after 6 weeks, we have only 729 people. Now that would still be more than linear. Like if I was just infecting 3 people more each week, this is still way more, but of course not as much as this table. So the next question asks us to compare. So through the magic of video editing, I'm going to pause the video so I can cap these tables, and I'll be right back. And we're back. What? Okay. So this question asks us, number 6 asks us to compare these two flu viruses. Of course, the red over here is a super aggressive 10 times infection. Over here is a less aggressive, only 3 times infection. So how are the data in the table similar? How are they different? Well, there's some really obvious similarities, right? So let's go ahead and track some of these similarities. The first thing you should notice is that both are growing, so they're both increasing. And I'm going to make this a little bit better answer. It's going to increases at a non-linear rate. And that's something we discussed ad nauseum today, right? So like the jumps here are not the same. They are times 10 every time, but the spacing, that's only 9 apart, that's 90 apart, that's 900 apart, that's 2 apart, that's 6 apart, that's 16 apart, sorry, 18 apart. So it's increasing, but it's increasing at a non-linear, and in fact I'm going to say increasing rate. So in other words, it gets bigger, and as it gets bigger faster. It grows and it grows and it grows almost out of control. Anything else that's similar? Well, I'm going to point out this thing right here. Check this out. Go highlighter. Let's go yellow. It's kind of interesting that both of them started at a 1. So it starts at 1. So that's another similarity. And I got one more for you. Both are multiplication. So in both cases, the tables change by multiplication. Okay, so differences. Well, things that are different. Well, which one is growing faster? Well, certainly the rates of what they're changing by are both getting bigger, but this one's getting bigger faster, right? Another difference, obviously, these numbers are all bigger than these numbers, which we kind of expect if this is growing faster, right? How would the two graphs of data? How would the two graphs of two data sets be similar? How would they be different? So let's talk about the graphs. And I'm not going to put the real graph on here, but I'm going to put a sketch. And I'm just going to kind of reflect about the things we had already stated. So in both cases, we're starting at 1. They're both going to be getting bigger, but we kind of expect this guy to get bigger faster. So instead of just kind of having a nice looping kind of curve, we kind of expect to go zoop very, very quickly. As opposed to this guy, which will get bigger, is getting bigger faster and linear, but not quite as fast. So that's kind of how those graphs are going to be similar and different. And it has a lot to do with the fact that this is infecting 10 people at a time. This is 3 people at the time. Oh, blank page. Okay, so number 5 and number 6. Now, these are related questions that have a lot to do with what we're doing next couple days, weeks in this section. So these are good questions to kind of puzzle over. So if you had trouble, not a big deal. Let's get to it. You were given $3 on day 1, and the amount you were given doubles each day. How much will you be giving on day 4? Guys, this is begging you to make a table. So that's what I'm going to do. So over here, we'll track the days. Over here, we're going to track the money. So day 0, well, let's not do that. So day 1, you have $3. Day 2, it doubles. That's going to give me 6. Day 3, it doubles. That'll give me 12. Day 4, that doubles. It gives me 24. So $24 is ultimately the answer. But let's talk about how we got there. It's really about the mode, the medium you were using to actually display your work. In this case, table works really well. Don't be afraid to make one, guys. We've been using tables pretty much forever. And the reason why is because they're so bloody useful. You guys want to know a secret? I use tables all the time to figure out math. Like, this is probably the most used strategy in the history of mathematics. This guy right here making tables. Look about number 6. Get out of here, red mark. Ah, boo. There we go. Okay, So number 6. Now this was a crazy question. When I saw it, I'm like, I don't know about this one, guys. But then I realized all you really have to do is think about the pattern. If you know the pattern, you know what's going on. So just check this out. For the situation in question 5, you can use exponents to write expressions like blah, blah, blah. Give the amount of money on each day. The amount of money you were given each day is as follows. So day 1, day 2, day 3, day 4. And then they want you to kind of figure out what expression you have in day 20. But what you really got to do, guys, is realize that there's a pattern. Check this out. I'm writing big. So this is day 1, and this turns out to be 3 times 2 to the 0 power. Okay, so this is day 2. Let's check. No, just that's 3 times 2 to the first power. Now, you should stop here and make a basic observation. What's changing? What's staying the same? Now, if you make that observation, you'll see right away that this is the only thing that's changing. So the question I asked myself, was that related to the days in any way? Well, check this out. That was day 1. It turned out to be a 0. That was day 2. It turned out to be a 1. So if you're following this pattern, I know you are because you're good thinkers. This is day 3. So we'll still have 3 times 2. Look at that. It's a 2. Kind of what you expected, isn't it? 1 less than the number of days, which means that that's going to be 3 times 2 to the third. 3, which is 1 less than 4. If I go to day 5, you expect that to be 3 times 2 to the 4th power. Day 6, you expect that to be 3 times 2 to the 5th power. So if I skip all the way down to day 20, we expect that to be 3 times 2 to the 19th power. So even though you don't know what the equation is saying or what the numbers necessarily mean, you can still find a pattern, guys, and that's really what this question is about. Can you find the pattern? So to exponential question for day 20 would be 3 times 2 to the 19th power. Now, why is this called an expression? Pause, ... Well, it's because there is no equal sign. This is not an equation, it's an expression because I can't solve it. Alright, guys, so I'm going to try to make sure I'm doing these videos regularly. I appreciate you guys watching them, helping yourselves out, maintaining that grade, do what you guys need to do. Do appreciate that, guys. So spread the word if this helped you. Thank you. So let people know. See you guys tomorrow. We'll do some more exponential work.
Con los terroristas.
And do the Harlem Shake.
Con los terroristas. Con los terroristas.
And do the Harlem Shake.